Hello everyone. Welcome to this webinar by YHS India. It's my pleasure to introduce to you today's speaker, Dr. Sarosh Ghausi. He's an assistant professor at Kotak School of Sustainability, IIT Kanpur. He received his PhD from Max Planck Institute for Biogeochemistry and Karlsruhe Institute of Technology in Germany in 2023. And prior to joining IIT Kanpur, he was a postdoc researcher at the Max Planck Institute for Biogeochemistry, and also he was a visiting researcher at Harvard University. He holds a master's degree in water resources engineering from IIT Bombay and bachelor's in civil engineering from Aligarh Muslim University. His research focuses on understanding water cycle, energy cycle, and their implications for weather, climate, and extreme events. And today he'll be talking about a very cool problem from land-atmosphere interactions perspective, the role of vapor pressure deficit. Is it a driver or a response in the land-atmosphere exchange? So welcome, Sarosh, and we all are looking forward to your talk. So without any further ado, everyone, let's hear from Sarosh.
Yeah, okay. So thank you, Tejasvi, for very kind introduction. I hope I'm audible to everyone, right?
Yes.
Yes.
Okay, great. So today I will be speaking about vapor pressure deficit, a driver or response of land-atmosphere exchange. But the goal of the current talk is basically twofold. So one is, of course, to basically showcase some of the work that I've been doing in past and also some of the work that I plan to do, but also to basically initiate a discourse about a rather murky topic, which is how much does VPD or soil moisture affect the land atmosphere exchange? And I will just show the details soon. Uh, so let's just first take a step back and even ask a broader question that why is land important for weather and climate? I mean, when we look at the atmospheric circulation, advection, parcels of air moving up and down, it's all happening up in the atmosphere. So what role is land is really playing? And one thing that land does is that actually land can dry out. So land doesn't always stay saturated, which basically limits the how much moisture we can exchange from surface to atmosphere. Second thing that land does, unlike ocean, is that it actually buffers a lot of heat in the lower atmosphere and not below the surface. So that's why we also clearly see a diurnal cycle in turbulent fluxes over land. And this heat and moisture exchange also varies across dry and wet regions. So for instance, if we have a wet region, more energy is actually partitioned into evaporating the water. And when we have a dry region, more energy goes into heating the air. So it also affects your near surface atmospheric variables. And the third is, of course, there are feedbacks which can basically exacerbate the extreme events, be it heat waves or floods. But the key line is that heat and moisture exchange from land to atmosphere actually play a significant role in shaping the near surface atmospheric conditions. So now let's come to vapor pressure deficit. So in case you don't know what vapor pressure deficit is, it is basically a difference between the maximum water vapor air can hold minus the actual amount of water vapor in the air. So essentially, if you have a saturated air, you have vapor pressure deficit of 0. And then you have an upper limit, which is mostly controlled by how heated the atmosphere is. And why is this relevant is actually when we try to model particularly the water exchange, a lot of approaches use VPD as an indicator to model evaporation in addition to the other energy-based approaches. But it also have implication towards plant physiological responses. So for example, it has been widely shown that when we have high VPD condition, the atmosphere is really dry and plants tend to close their stomates, which reduce the evaporation. And this stomatal closure is usually modeled like using various fundamental models, the Ball-Berry model being I think the earliest one of them. But then there is also soil water limitation. So what if the water is not limited at the atmosphere, but it is simply a lack of access to water from the root zone? Then soil water limitation also affect evaporation in different ways. So generally, this is basically a classic approach by Sonius and Uretne in 2009 paper, where basically it was shown that evaporation essentially have two regimes, a water limited regime and an energy limited regime. In water limited regime, any change in soil moisture affect evaporation rates. And in an energy limited regime, essentially the soil is decoupled from the evaporation. So it's almost just the energy which is driving the evaporation rates. So high soil moisture usually refer to energy limited conditions and low soil moisture usually refer to water limited conditions. But things get quite complicated here because there is also a strong coupling between soil moisture and VPD. So essentially when you have low soil moisture and you are in a water limited evaporative regime, you also put more heat into the atmosphere, which I showed in my previous slide. And that heat enhances the VPD because VPD essentially also depends on maximum water vapor that air can hold. And this confounding effect uh, gets very tricky to really disentangle the driver of evaporation from VPD and soil moisture. So I will be broadly talking about these effects in my talk. But before that, I just introduce the modeling approach that I use. So basically, I deal with the moisture and heat exchange, not explicitly the gas exchange. And these interactions are confounded by different atmospheric and land surface conditions. So for example, you can have cloud cover, VPD, advection. At the same time, you can have different quite heterogeneous land surface characteristics with different soil moisture, vegetation, and albedo. Now, but there is one thing is common that almost all these affects the energy balance of the Earth system at some point. So I essentially use four major constraints. The first is I look at how the energy is changing at the surface. So the surface is heated by solar radiation, and this heat is basically being released into radiative cooling by surface. Some heat goes into the lower atmosphere in sensible heat, and some simply goes into evaporating the water. Then we can also write an energy budget for the lower atmosphere. So if we make a simple box close to the surface, we look at how the energy flux is changing within that box. So there are both directions. So energy is also coming from the surface and it's also leaving through radiative cooling at the top of the atmosphere. And then one can also write energy balance or rather imbalance at the top of the atmosphere, which is how much solar radiation is coming in at the top of the atmosphere and how much is going out. Generally, if we don't expect any kind of transport, we would expect these two terms to be equal, but that generally never happens because there is always some horizontal exchange which basically leads to an imbalance. And together, both B and C tell us information about heat storage and heat transports. And then the fourth is rather non-trivial constraint which I use is basically a thermodynamic constraint on turbulent fluxes, where I assume that the turbulent fluxes are actually operating at a thermodynamic limit of maximum power. So just I would first briefly describe what this constraint is. So essentially, the whole idea is that turbulent fluxes requires motion. And is there a maximum limit to how much motion we can generate out of a given temperature difference? So we conceptualize the surface atmosphere system as a heat engine. And this is basically built up on several previous works. For example, Kerry Manuel at MIT, he started with modeling hurricanes as a thermodynamic system. Then Paulus and Held also have the following papers where they try to model moist convection as a heat engine. And then Axel Kleiden has been applying these concepts to understand the land atmosphere exchange. So basically building upon that, what we did is that so basically we conceptualize the surface atmosphere system like this heat engine and we calculate how much maximum work we can generate to sustain motion. And this motion is, what basically drives the turbulent fluxes or let's say sustain the turbulent fluxes. Then when I'm not showing the equation, but when we write a set of equations, we essentially basically get to this limit, which I call it as modified Carnot limit. And I call it modified because it have a heat storage term in it.
He seems to have disconnected.
Yeah.
Let's see, he'll rejoin.
Sorry, I think my internet kind of just went away.
No problem. You can share the
So
screen
you
again.
can,
Okay, yeah.
can anyone of you just help me? Where was I last time? Where I?
Describing this modified Carnot limit.
Okay, great. Yes, so basically the idea is that I think one point that I want to emphasize was that unlike the conventional power plants, here the temperature of the hot source and the cooler atmosphere is not a fixed property of a system, right? So the more turbulent exchange we have, we also reduce the driving temperature difference because we cool the surface with more evaporation and more sensible heat. At the same time, we heat the atmosphere with more condensational heating happening in there. So this actually leads to quite a different trade-off, which we call it as the maximum power limit. And one can basically optimize and do a numerical solution for this limit, and that gives us turbulent fluxes as a function of radiative forcing. And what I then basically showed that atmosphere seems to work closely at this limit, because when we compare the turbulent fluxes derived from maximum power, it compares quite well with, I show here the comparison with ERA 5, but it also works quite well with FluxNet and FluxCom and other observation derived data sets. And it essentially explains two major things. The one is that it explains why turbulent fluxes reduces with aridity, and second, which also has to do with the driving temperature difference. But it also explains why there is a compensating role between water and heat exchange. So basically, when we have a dry surface, why sensible heat actually picks up, and when we have a wet surface, why sensible heat basically comes down. So this compensating effect is also very well explained, and the reasoning is simply because the total turbulent fluxes are constrained. You can't basically generate more free energy than the thermodynamic limit. And then the last application is one can also calculate the effect of clouds over dry and humid regions, and it basically have quite major implications for land surface models, because essentially what it shows is that wind shear is not the only driver of turbulence, but local buoyancy can significantly contribute to the local turbulent fluxes. And I think this is particularly relevant for tropics because we have a very strong solar forcing here, and wind shear driven turbulence model clearly needs to be reevaluated. Okay, so now just moving forward, so I basically use the same kind of model principles essentially, but try to model a different variable, which is a diurnal air temperature range. So diurnal air temperature range is basically described as a difference between daily maximum and daily minimum temperatures. Uh, and then one can basically just formulate a similar model. And then we hypothesize that the diurnal variation of air temperature is mostly reflecting the heat input in the lower atmosphere. And based on this, we get an expression for DTR, which is not so relevant, but what is relevant is that we have an equation of DTR as a function of surface water stress, which is essentially a ratio of actual to potential evaporation, which tell us how dry or wet the surface is, and radiative forcings, which is RS, RLD, and RL2, essentially solar long wave and outgoing long wave forcings. Then basically I use this model to understand, okay, so how does DTR actually changes with different surface and atmospheric conditions. So here in this phase space, what you are seeing, the x-axis is a water limitation factor. So it tells us how dry or wet the surface is. The higher the value, the wetter is the surface. The y-axis is a clear sky fraction, which essentially means the lower the value, more cloudy is the atmosphere. And what we see is that the DTR actually have gradients along both directions, right? So DTR also reduces with cloud, but DTR also reduces with water stress. And this, the top figure is essentially the model response from the equation that I showed you before in the previous slide. And the bottom figure is the response that we see in observations from FluxNet. So you can see that it is, very nicely basically capturing the effect. Essentially, the key highlight is that you get that highest DTR when you have really dry atmosphere and a really dry surface. So both surface and atmosphere contribute to a higher diurnal air temperature range. One can then isolate these differences and calculate also how much DTR is different due to clouds and water stress. So of course you can see that DTR actually have a greater reduction with clouds compared to water stress, but water stress also, play a significant role. And now this have one very critical implication, because essentially what it shows is that near surface atmospheric observations like diurnal at temperature range have imprints of soil water stress. So one can invert this relationship and diagnose soil water stress from the diurnal air temperature range. And this is something which, have been one of the key thematic areas of a lot of recent research, where they try to use near surface atmospheric observations to diagnose surface water stress information. And this paper also just appeared in GRL, so if you want to take a deeper look. Okay, so now I'm slowly coming to my key topic that I want to address, and that is how much variations now in VPD are controlled by thermodynamics. Now, I think the first thought you might be thinking is why I was talking about temperatures and more of the heat balance, and suddenly I'm talking about VPD. So let's just look essentially again what the VPD was. VPD was a difference between saturation vapor pressure, that how much moisture the atmosphere can hold, minus the actual amount of water vapor in the air. And when we look at a typical diurnal cycle of VPD, it also shows a very nice diurnal cycle, right? So almost like a temperature. And the reason is simply that the saturation vapor pressure, which is basically the maximum water vapor the air can hold, is actually a function of air temperature. And this is widely known. This is known as the Clausius-Clapeyron equation. Okay, so now what we can do is, so we also have a diurnal air temperature range, which I just showed in the previous slides. We have an expression for DTR. The next question is, can we predict VPD from DTR? So just how much variations in VPD are occurring solely based on changes in heating? So this was the primary motivation. So can we predict the vapor pressure deficit using DTR? And here I write VPD max, basically a daily maximum VPD that is reached during the day, as VPD min, like a minimum VPD at night, plus the diurnal change in VPD. And then the diurnal change in VPD can be written as basically d Z by dt, which is the slope of saturation vapor pressure times the diurnal air temperature range. The advantage is that now we essentially have a expression for VPD as a function of radiative forcing and water stress, similar to that we have for DTR. And when we compare this expression, so this comparison is over the FluxNet sites over Europe with more than 150K days of data. And it basically shows that it really works quite well. And then one can also upscale it using gridded data sets. And here also you can see that this is the VPD observed and the right figure is VPD estimated, which again basically reproduce the spatial variability very well. Okay, so now the next step. So now we get an expression for VPD. Can we decompose it into different drivers? So let's say now what I want to do is I want to understand, we know how much radiation is contributing to heating. I know how much water stress is contributing to heating. Can I decompose how much it is contributing to VPD? So here what I'm showing is a decomposed VPD max into the three drivers. The first driver is radiation, which essentially means when you have more radiations, you have a higher VPD. The second driver is water stress, which basically means that when you have a water stress or a dry surface, you put an extra heat into the atmosphere, and that extra heat generates an extra VPD. So this is basically that VPD. And the last VPD is VPD min. Now this VPD min can be thought of as a baseline moisture limitation, and which is most likely a result of this large scale subsidence or basically the descending branch of Hadley cell that we see. So just to give you an idea of their relative contributions, so if we look at the zonal variability, the black solid line that you can see is the VPD estimated from our model, and the dotted line is the observed VPD. So we are able to basically capture the zonal variation of VPD really well. And then the figure just below is essentially showing the decomposed components. So there we see that actually it's the VPD radiation which is kind of predominating almost everywhere, but it's still, it's almost a comparable contributions from water stress as well. We can see there is a spike at the subtropics, and this spike is due to different reasons. So for example, we see a spike in radiation in the subtropics, and that is simply because of less clouds and more radiation coming in. While in the water stress also we see a spike, and that is simply because of two factors. The one is a water stress effect, so basically low evaporation, more heat into the atmosphere. and the other is a baseline moisture limitation effect, which is a result of this large scale subsidence. Then one can also, just plot it in the more of like a percentage VPD explained way. And there we can see that, except from the subtropics, almost 70 to 75% of VPD can be explained by radiation alone. But in the subtropics or in dry regions, it's almost like a 50-50 contribution. So if you just add up the VPD main and the water stress component, it's almost comparable, both the terms. So the key highlights of this figure is, okay, zonal variation is well captured. Radiation dominates VPD in humid regions and comparable radiation and moisture contributions in arid regions. Okay, so now I'm coming to the hard part of the talk. The first I start with basically showing a simple thermodynamic models that can predict temperatures based on how the energy is changing. In the second part of the talk, we link this heating to VPD changes, and we show that it actually captures VPD quite well. The third part of the talk will focus on the VPD responses. So how VPD relates to the land atmosphere exchange and what implication does this model have on it essentially. So this equation is basically this Feynman-Monty, one form of Feynman-Monty equation, where evaporation is written as a gradient in a water vapor. GA is the aerodynamic conductance, which is mostly a function of wind speed. But there is another term which is called the surface conductance. And this surface conductance is a really tricky term because it depends on VPD. So if you have a well-vegetated surface, your stomatal closure can modulate this surface conductance. But it is also controlled by soil moisture variations. So I'll just show how. So this all started that when we do leaf scale experiments, what we find is that when you increase VPD artificially, plants tend to close their stomates. And this stomatal closure leads to a decline in the stomatal conductance with VPD. So you get this like kind of a monotonic decreasing surface conductance VPD relationship. Now a very interesting paper came out in 2023 in Nature Water by a colleague. And what he shows essentially is that if we use salt flats are regions which essentially have an active hydrological cycle but have no vegetation at all. And there also they were able to reproduce the same conductance VPD relationship that you would expect a plant to behave, except that there is no vegetation, right? And then again, it leads to a question that, so why does soil moisture alone is able to produce kind of this stomatal closure kind of relationship? And we provide a possible pathway for it. And that pathway is that essentially when you have a more surface water stress or a dry surface, you put more heat into the lower atmosphere, you increase your diurnal air temperature range, and that diurnal air temperature range further leads to a higher VPD. And this can be shown on basically a sample FluxNet site. What I essentially show is that if you look at the red, it is purely observations of surface conductance and VPD. And the fitted line is basically a Madeline model fit, which is also a stomatal conductance model. The blue line is basically the estimated response from our model, and the fit is a Madeline style fit, right? So essentially, what I'm showing is that we get a Madeline style model fit without explicitly telling a model to close stomates, right? Or there is literally no vegetation parameterization going in, but essentially you can get this relationship just by the effect of surface water stress on DTR and its effect on VPD. Okay, so this is one application. The other application is, in general, a non-linear response to evapotranspiration. So again, when we look at the leaf scale experiments, they show that when you have a higher VPD, evaporation kind of first increases, but then once the basically vegetation gets stressed, then plants tend to close their stomates, and then we get this negative relationship. So like a hook-shaped curve. And then what I show here is that, okay, let's just talk about soil moisture dynamics. So remember that I talked about there are these two regimes. We have water limited and energy limited regimes. These are quite relevant because when we talk about atmospheric heat storage or heat input in the lower atmosphere, when you are in a water limited regime, when you have less evaporation, it will lead to more heat, right? Because less evaporation, more heat. Because of increasing sensibility. But when you are in an energy limited regime, then the correlation between evaporation and heating actually becomes positive. So when you have more evaporation, you have more heating, simply because more evaporation is simply meaning that you have more radiation coming in, right? And this essentially then have implication for DTR. So you get a higher DTR with higher VPD with decreasing evaporation in a water limited regime, while in an energy limited regime, you get a higher DTR with higher VPD with increasing evaporation. And one can then get a similar kind of this hook-shaped relationship that you get from the leaf scale experiments. So I mean, again, it's not that saying that leaf scale experiments are wrong or plants doesn't close their stomates. It's just showing the intensity of a confounding effect that you can get the same response from soil moisture as well. So when we are mostly looking at the ecosystem scale, we really need to pinpoint the drivers, whether it's coming from soil moisture or is it a VPD plant interaction. This plot is essentially showing the same thing, but more in a quantitative manner. So basically, I created a phase space. So if you plot evaporative fraction with solar radiation, you get two regimes. The one regime is an energy limited regime where your evaporation increases with solar radiation. The other regime is a water limited regime where your evaporation reduces with solar radiation, right? Uh, and in this phase space, when you plot simply like correlation between VPD and LE, what you get is you see this clear divergence. So in an energy limited regime, VPD and LE are actually positively correlated, and in an water limited regime, they are negatively correlated, right? And so A is essentially using purely observations. But what I show in this figure C is a modeled response, which is simply showing relating water stress to DTR and DTR to VPD. And that is able to produce this basically contrasting response very well. So, okay, so now last part is of course like, so what, right? What does this mean? What does this imply? And it is quite relevant because if we look at the VPD changes or VPD projections, VPD is kind of increasing everywhere. VPD is, this is already just looking at trends. Paper just came out in Nature a few weeks ago. But even VPD projections are like VPD is going to increase everywhere. But when we look at soil moisture changes, they are highly variable. So because soil moisture essentially follows rainfall, and because rainfall is quite variable, so in some regions soil moisture is going to increase, in some regions soil moisture is going to decrease. So it becomes quite critical to understand how these two affects the land atmosphere exchange. And this discrepancy have always lead to quite, contrasting studies. So for example, there is this study which basically shows soil moisture dominates ecosystem production, but then there is another study which shows VPD dominates ecosystem production. Similarly, there is another study which shows that you get a surface conductance VPD relationship without in absence of plants. And then there is another paper which basically shows that there is an increasing importance of VPD in water and carbon fluxes. It also have implications for aridity. So basically, if you use a soil moisture or land surface based indicator, you reach to a conclusion that there is no projected global dryland expansion with global warming. But if you use a VPD or atmospheric aridity based indicator, you basically reach a conclusion that there is an accelerated dryland expansion into climate change. So just trying to show that there are this confounding effect that needs to be addressed. And what our approach offers here is that it basically one is that it provides a physical characterization of periods where VPD acts as a driver and as a response of land atmosphere exchange. It has implications to understand soil moisture VPD coupling and also to evaluate aridity changes and drought responses. So I think this is mostly what I want to talk today. I also work on extreme rainfall sensitivities, which I will not be speaking here, but if you are interested in having a discussion about extreme rainfall changes, I'm happy to discuss it anytime. Also, this kind of approach that I show, this thermodynamic approach, it can also be applied to understand temperature extremes and heat waves event and to characterize different kinds of heat waves event. This is also some work which I closely did with a colleague, Yingling Tian. And last but not the least, so I started this new position at IIT Kanpur as assistant professor at Kotak School of Sustainability, which is basically India's first fully dedicated school on sustainability. And I will be starting my research group focused on terrestrial hydroclimate theory and modeling. And the overarching goal of the group is to basically use theory, observations, and modeling to increase the representation and basically the simulation of land surface processes over India. Uh, yeah, so I mean, if you are interested in this or want to have a chat, just feel free to shoot me an email anytime. I think that's all, and thank you so much.
Thank you, Sarosh. Thank you for this very nice talk. Now, let's open this session for questions from the audience. If anyone has any questions, please raise their hands. And
Shall I ask the question? Okay, someone is raising the hand.
yes, Ankit, yeah, you can please go ahead.
Yeah, thank you, Sarosh, for the. I think it was quite a unique presentation. I've never looked at VPD through thermodynamics. It was great. Leading to your, I think couple of previous slides when you had this soil moisture and VPD
Mm-hmm.
impact on ecosystems. I've always thought that VPD is kind of a high pass filter and soil moisture is kind of low pass filter, or the other way
Yeah,
around. And the
yeah,
impact
yeah,
the ecosystem are basically fluxes at different time scales. Okay.
yeah.
VPD being more dynamic, it has a lot of intraday variation, but soil moisture has a larger legacy effects kind of things,
Yes, yes.
which I have felt when I was looking at the data. But what I wanted to ask you is, when you looked at your studies, like the one that you showed, you tried to explain the VPD variations using DTR. Did you use? Did you also use data at daily resolution, like
Yes, yes.
interannual as well?
Yes, so I think just quickly coming to your two questions. Yes, I mean I use daily data there, uh,
Okay.
and I think yes, I completely agree that there is a time scale lag in it, right? Because soil moisture takes time to react, where VPD plant interaction can be quite fast. But I think it affects the clustering of points. So I just put on in this slide because this right paper that came in, it also used half hour flux data.
Mm-hmm.
But I clearly agree that. But I think if you look at the clustering of the points, then you will basically get a long-term signal there. Uh, so maybe the points in the left and right in the VPD curve of stomatal conductance may reflect to very similar time steps, but in the soil moisture, I mean, they would be much far apart, right? Uh,
I mean, this is, I mean, from the left figure, it's quite clear. If you have different wetness, like you have 0.3, 0.5, 0.7,
yes,
the Orion curve actually changes and you see a
yes.
different slope. That's quite clear. Um, but I was wondering, like, when you try to decompose the VPD, uh,
Mm-hmm.
you also did use the half hourly or the hourly data set, right? Or was it at a
No,
different?
we use daily data,
Okay.
right? So
Not half hourly. Okay.
essentially, yes, it is because we use GTR, and so the idea is that we use the difference between the maximum and
Yeah.
minimum temperature, and we say that this is the heat input in the lower atmosphere, and then we link this to VPD. So, I mean, in principle, uh, I think we don't yet have a theory for diurnal evolution of temperatures. I
So
think once
that has
we
been
have
going on
that,
for quite a long, because when you model a flux, you want to also include VPD and temperature, because those two are like physically different things, but they're very correlated at a diurnal
yes,
scale. And I was
yes,
very interested to see that you somehow decomposed it, but maybe we have to really look into how we decompose that when we want to model flux at a diurnal time scale. But I think, but this is still quite great. So at a daily time scale, you can say that this much. Suppose you want to model carbon flux or water flux, okay, of
yes.
an ecosystem. Now you have temperature that you use, a daily mean temperature. You have daily mean VPD, but you can also have the VPD that is due to water stress as a different factor, right? And you can also
Yeah.
use that to explain what is the impact of this additional VPD water stress that is in like impacting the flux. That
Yeah.
that you can also still do with this method of yours, right?
Yeah, I think so. I mean, clearly we need to segregate the applications, but so I mean, if you are talking about this, I mean, CO2 assimilation rates and all, I mean, at the much granular scale, this, I mean, I don't know how to what extent this will hold, but I mean, if you look at the, like, for example, projection of aridity, right, or VPD drought responses or the flash drought responses, and or even at the, I mean, simply when we look at this ecosystem scale conductance evaporation relationships and try to get some relationship from machine learning and use that relationship to upscale flux in some different region. I think all these studies are basically on a longer time scales.
Yeah.
And there we need to basically really separate out the effect of, plant physiology and the soil moisture dynamics.
True. Okay, but yeah, very excited. And all the best with your
Yeah.
new position. And hopefully we'll be in touch soon. Thank you
Yeah,
for the
definitely.
answers.
Thank you, Ankit. Thank you. Thank you. Thank you.
Very nice. Pankaj has a question. Pankaj, you can go ahead and ask it yourself.
Hi, Sarosh.
Hi, Pankaj.
Uh, very nice presentation. Can you go to slide 10? I have a few questions from there.
Okay. This.
Yeah, so these plots, are they change in VPD or is it the VPD absolute?
No, this is absolute daily VPD.
Okay. But in this
Yes.
equation, you have written like VPD max equal to VPD mean plus the change in diurnal VPD.
Yeah. So I mean, this change is basically VPD max minus VPD min, right?
Mm-hmm.
So essentially, it's like, I mean, delta VPD is VPD max minus VPD min. But I write it diagonally because VPD max minus VPD min relates to T max minus T min, right? And
Yes.
times the slope of saturation vapor pressure. And Tmax minus Tmin is DTR. And we have basically this theory for DTR that it reflects heat storage changes. So from there, we get basically an expression for delta VPD, which is basically saying that delta VPD is also mostly reflecting the heat storage changes times how the saturation vapor pressure is changing along with that heat storage.
Okay. And in one of the slides, maybe in 11 or 12, there is a relationship between VPD and stomatal conductance. I think where it is. Yeah, this one. So I was seeing this figure and I was thinking whether can we explain vegetation patterns from this plot. For example, suppose you are in savanna climate where all the vegetations tend to cluster in one zone. Suppose you get this curve and you try to explain the organization in this vegetation. For example, the curve, the parameters can explain the size of the clusters of this vegetation, how clustered they are in space. Is it possible to look it from that perspective, from this data?
I mean, I think that let's say this soil moisture effect wasn't there in principle. If it was solely a VPD plant interaction, then I think in principle one can, I mean, just do some kind of clustering of different vegetation types based on how they respond to how VPD and stromatal closure responds, right? But I think it gets complicated because we have an additional effect of soil moisture, and there it gets tricky because, I mean, for example, you have deep rooted and shallow rooted plants,
Yeah.
and both deep and shallow rooted plants have different basically a deep rooted plant can remain in an energy limited regime for a long time than a shallow rooted plant, right? So I mean, I'm not sure how to bring these two things together, but I mean, I think clearly there are avenues where one can do some kind of clustering of vegetation type based on responses.
Okay. So my another question is like the basics of this. For example, suppose I want to learn more about the what kind of work you are doing. So where should I start? Suppose where first of all, like do we need a very good understanding of thermodynamics, or can we just directly go to all the
So-
technicalities that we're having?
No, so I think thermodynamics is more like so basically like I've been working on thermodynamics during my PhD, and then basically applying the same frameworks to study land atmosphere interactions kind of. So I mean, it's not entirely inclusive that you both things go hand in hand. I think this is what I presented here is like more like land atmosphere interaction work. So I think there are some classics papers that I can maybe send you, which basically can good framing of these ideas. About thermodynamics, I would suggest that I mean, again, there are a lot of content, but I think Excel has a book, Thermodynamic Foundation of the Earth System, and which I think is really nice, but it's quite big.
Okay,
Yeah,
thank you,
yeah,
Sarosh.
yeah. Okay, Pankaj. Thank you.
Great. So do we have any more questions? So Surya has one question. Maybe you can go ahead, Surya.
Sir, it's a nice presentation. I just had a very basic doubt whether when we consider the VPD, whether we have to consider the below canopy or is it the canopy in the field scale studies?
So sorry, Surya, can you repeat? I didn't got your
Yeah,
question.
my doubt is like whether we need to consider the VPD below canopy or above canopy in case of field scale study.
Okay. VPD below canopy, above canopy. I think, yeah, I think that's an interesting question. I mean, intuitively, I would think if you're, I mean, dealing with the VPD plant responses, then it should be above the canopy. But the soil moisture VPD interaction, I think, would occur. I mean, it necessarily doesn't uh, uh, depend on canopy information directly. But I mean, it partly does because I mean, you also have water exchange above the canopy, and so yeah. But I mean, that's an interesting question. But I don't know at what if the results will change at the uh, canopy scale. Yes.
I have some questions. Sarosh.
Yes, Avinash.
Yeah, a nice presentation. In your slide number 11, you showed VPD over different latitudes.
This.
Yes, here actually, you mentioned like there are some reasons why there's a dip in equator. But
Yes.
is the signal like because usually northern hemisphere we have more land area than southern hemisphere, right?
Mhm.
Is that signal also visible here, some extent?
I think it is. I mean, uh, I think partly it should be, uh, but I think this is only scaled over land, so perhaps it
Okay,
doesn't matter much. But I mean, if we use composite uh, like layers, then perhaps it would be much clearer.
okay, right. And one more question, like I don't know whether it makes sense, but I'm more interested in the thermodynamic perspective uh, towards this extreme event
Mhm.
with the warming climate and I'm more interested in this upper phase,
Mhm.
high precipitation extremes, right?
You mean
So can you
extreme
comment
rainfall or
extreme precipitation events? Yes, uh,
okay.
with global warming. So I'm just curious, like, can we bring some perspective from this thermodynamic point of
I
view?
mean, there is clearly. So I have these two works on extreme rainfall where uh, essentially, I mean, it's a quite specific work, but because in the end, it's a thermodynamic effect, right? Because the moisture holding capacity of the atmosphere crosses Clapeyron equation. It comes from thermodynamics, and also, I mean, there are papers like the one that I was talking about, Kerry Manuel, where he basically modeled hurricane as a moist heat engine, and I think he did this in 1991, and at that time he derived sensitivities which basically matches really well with even the model projections now. And I think the whole idea is that how much maximum intensity rainfall can have, right? And does there exist an upper limit to it regionally? And I mean that would be a key question. And the other question would be, of course, if we get to that limit, then how that limit changes with temperature. If we have an analytical solution, one can do that. So I mean, I think we have our work on it, which I don't show here. But there is also other part where thermodynamics can come in extreme rainfall sensitivity. So for example, this work that I did is mostly about that whenever we use observations to derive extreme rainfall sensitivities, we assume a one-way causality. We assume basically that it's temperature which increases the moisture holding capacity, and then that larger moisture will bring in more rain. But there is a other side to it, and that is that with more rain, we have more clouds. And more clouds means they will cool the surface, right? So there is a covariation of rainfall with temperature through this cloud effect. And this model, which I basically showed in my previous slides, can be used to disentangle this effect, and then it have quite a major implications for extreme rainfall sensitivities. So essentially what we show is that when we account for the cloud effects, we get sensitivities which are much consistent with Clausius-Clapeyron scaling.
One more question, like so far you had shown your results. I see it's a larger spatial scale, right? Like global or continental.
Yes.
I'm just curious, like when I'm talking about rainfall extremes, we want like more localized, like a basin scale. So there, I'm just curious, whether this
Yeah.
thermodynamic point of view has any role.
Yeah, I think, I mean, the problem of scales is more related to also, I mean, having data and the right downscaling at that scale, right? So, uh, I mean, in principle, if we have observations and if we have one isolated storm and which is well monitored, then clearly I think one can apply thermodynamics and try to understand what were the limits that shaped that storm. But again, for that, we need really a well monitored isolated storm, right? And so in that context, I think it's more like a data limitation, rather than applying the approach.
Thanks. We'll be in touch.
Yeah, definitely.
Yeah, thanks a lot.
Okay, I think we don't have any more questions. If anyone has any questions, you can please press the raise hand button in the interface. In case we don't have any questions, so then let's all thank Sarosh for this wonderful talk and wonderful interactions that happened in this talk. And I encourage you all to share YHS India's this web page or social media handles to your groups. Ask other students to join so that these interactions are really helpful. And we'll see you all soon with the next webinar. Please, I think you all have already subscribed to the email, so we'll share that soon. Thank you, Sarosh. Thank you for this wonderful talk,
Okay.
and see you all in
Yeah,
next
sure.
webinar.
Thank you, Tesri. Thank you, Vinesh, and thank you all the YHS organizers for having me. And yeah, maybe see you again at the next YHS webinar. Okay, bye-bye.
Bye-bye.
Thank you, everyone. Bye bye.
Bye. Bye, Ankit.